I had promised to provide this as a video in addition to what we did in class. So let me go ahead and fulfill that promise now. This is the second part two of the videos that on just a review of statistics. And I want to talk about probabilities here. As you can see here, this is not covered in chapter 11. That's for a future revision of that book. So I'll always, again, mention why we need stuff. So why do you need to know about probabilities? Statistical significance is a matter of probability. P-values and alpha are probability. So obviously we need to talk about probabilities. There are several axioms you need to know when it comes to probabilities. Probabilities range from 0 to 1. So if we let A be an event, so we use A as a generic, I don't know, variable. So the probability of A must be between 0 and 1. That's it. So that's just to make sure you know that. The probability of the entire sample space is equal to 1. And there's all these different events that can be within a sample space. Like, for instance, if we flip a coin, that's like random experiment. The outcome of that experiment can either be heads or tails. Probability of each is 0.5. So probability of S, the sample space, has to add up to 1. So if we add the individual probabilities together, 0.5 plus 0.5 is 1. And this goes for any sample space. Sample space is the space of all possible events in a random experiment. Could be whatever, right? Could be picking individuals and getting their depression scores from a population. The complement of an event is the event not happening. Okay? Complement of an event is the event not happening. If we let A be an event in the sample space S, let A with a line over it be the complement of event A. We'll call that not A. If the probability, if, sorry, if PR A is the probability of event A, the probability of the complement of A is 1 minus the probability of A. So thus we have the probability of not A equals 1 minus the probability of A. Right. I'll give you an example. If the probability of winning a game is 0.4, the probability of losing the game, again, this is a world where our sample space only includes two possible outcomes, winning or losing. It's 1 minus the probability of winning. So it's 0.6. 1 minus 0.4 is 0.6. Probabilities of disjoint events can be summed. These can be added together. If A and B are two disjoint, mutually exclusive complementary, that they'll mean the same thing. Events, disjoint means it cannot occur together. Then the probability of A or B occurring is the probability of the union of the two events, which is probability of A plus probability of B. So this is actually uh, this equation is just like a part of the the addition rule in general. The addition rule has accounts for the possibility that two things can co-occur. Excuse me. Let's talk about the normal distribution. Why do you need to know this? All variables have distributions. The statistical tests researchers choose depend on the variable's distribution. The normal distribution is the most important and common distribution. It applies to continuous variables. I say generally because we can transform variables that are not continuous. And then under the right circumstances, their distributions will converge to normality. By the way, that's Piper in the background. If you hear a strange noise, he likes when I'm talking. He wants to get involved. Has a characteristic bell-shaped curve. You can see right down here, right? Characteristic bell-shaped curve. The parameters, every distribution has what are known as natural parameters, and the natural parameters for the normal distribution are mu and sigma square. Mu is the mean, and sigma squared is the variance. These are population values because they're Greek letters. Other characteristics, it's symmetrical about the mean. 50% of all values fall below the mean, 50% fall above the mean. You just see it looks beautifully symmetric. The This is a continuous variable, and all continuous variables have what are called probability density functions versus say a discrete variable which has a probability mass function. So the probability density function for the normal distribution is this beautiful function here. If we integrate over that entire function from negative infinity to infinity, this would equal 1 because it it's a probability, the sum or integral, if you will, of all possible values in a sample space must equal 1. If you're interested in the proof, I have the proof here. You can click that. You have this already, of course. But this is available in my YouTube channel. Standard normal distribution is just a standardized version of the normal distribution with a mean of 0 and a standard deviation of 1. You could also say variance because the square root of the variance of standard deviation, square root of 1 is 1. So let's look at calculating probabilities and the area under the curve for standard normal distribution. What is the probability that a value z is below the mean? Well, that's not a hard one to solve because, excuse me, the area under the curve, this area here represents probability. You can see that at 0, this obviously has the highest, this is the highest point of this curve. So this is where we maximize the probability. It's the mean level in this standard normal distribution. But the probability of being below the mean is 0.5, 50%, because this is symmetrical, right? So if we could say the probability that z is less than 0 is 0.5, probability of z being greater than 0, and z in this case is a standardized value where we take in this case, we're taking one value, right? A person, say, and subtracting that person's, subtracting the population mean score from this person's score and dividing it by the standard deviation. What we're doing here is removing the natural scales of whatever the variable is and putting it in this if you will, this standardized scale that goes in standard deviations, right, from the mean. So you know that the probability of being less than, well, the 0 is the mean, so the probability of being less than, or actually is less than or equal or less than is the same because of the probability of any one point on a continuum is 0. So the probability of being less than 0 is 0.5, or being above 0 is 0.5. And if we wanted to know what's the probability of being either above or below 0.5, we're using all these axioms that we saw before, right? Like the sum of these complementary events is the probability of either of these two complementary events being above or being below 0 is a sum of their individual probability. So 0.5 plus 0.5. We know that the sample space must equal 1. These are complementary events. There's a lot of stuff going on there. The empirical rule is one that's very helpful because it allows us to answer a lot of questions about a distribution. Some people like to call it the 68, 95, 99.7 rule just because you want to remember it. So this is something you should know. So 68% of all values fall between plus or minus, so it's either side of the mean, plus or minus one standard deviation of the mean. 95% of all values fall between plus or minus two standard deviations of the mean, and 99.7% of all values fall between plus or minus three standard deviations of the mean. So there's Piper chatting on one end, my cat is snoring out loud behind me. Oh my. I just noted here that Chevyshev's inequality is an alternative to the empirical rule that applies to all distributions, not just a normal distribution. Empirical rule applies to the normal distribution. This figure shows the empirical rule, right? So this is the 68%. The area under the curve here represents 68% of all values, also represents the probability, right? Probability being between -1 and 1 standard deviations from the mean is 68%, right? Or 0.68. What's the probability that one scores? So I went through these different values here just so because of symmetry, these become relatively easy to solve. Like, what's the probability one scores between 0 and 1 standard deviation above the mean? Well, we know that 68% of all values are between ±1 standard deviation, and this is symmetrical. So between 0 and 1 would be half of 68, which is 34%. What's the probability that one scores at or below 1 standard deviation above the mean? Well, so you have to add two things together. We know that the probability of z being less than 0 is 0.5 because it's half of the distribution. And the probability between 0 and 1 is 0.34. So 0.5 plus zero point 0.3 is 0.84. What's the probability that one scores above 1 standard deviation above the mean? Well, that's just a complement of being at or below 1 standard deviation above the mean. So that's 1 minus 0.84 is 0.16. What's the probability that one scores below 1 standard deviation below the mean? Well, it's by symmetry, that's basically like below 1 standard, this area here, right? The same as this area here. So it's 0.16, right? So it's the same, but it's just on the other side. We can calculate percentiles. Percentiles are the proportion of values that are at or below a person's score, right? For instance, when we have a standardized test, we can compare any person's score to the population, so long as we have the population mean and the population standard deviation. And if we standardize the individual score, right, so we're putting them in this standard normal distribution form, we get the standard deviations away from the mean. So, for instance, here, probability of scoring at or above, oh, sorry. In 2017, the United States population mean and standard deviation, in parentheses, for the SAT math test was 527, 107 standard deviation. If an individual scored 490 on the math SAT, what's the individual's percentile rank? Same as the score here. So what I do is I convert it to the standard normal value, right? So I can use the standard normal distribution. I get this individual is 0.34579 standard deviations below the mean. So this is the probability of being less than or equal to this value is 0.3632. Okay, so what proportion of the population scored above our participant? So this person's percentile was 0.3632, or she scored at or above 36% of all individuals. Then what proportion scored above her was just 1 minus that with the rule of complementary events, so 6.6368. All right. So you see how I went through that process. I just pulled up a Z table. I used this one from the University of Arizona because it had all the values there. Just in case you need to know that when you use one of these tables, in general, what you'll get is the Z-score. And what you find here is the proportion of individuals, well, basically the percentile. What's to the left of the Z-score, right? That's the percentile. And you'd read this like for instance, if you had a Z-score of minus 0.39, could be 0.390, 1, 2, 3, 4, 5, etc. That's how you read these. And you find whatever the value you're looking for is. For us was what is it, 0.35. And usually these just go to two decimal places. So I found it at 0.36317, right? Or 0.3632 is what I had in the original notes. All right, so let's get back to work here. And confidence intervals. Why do you need to know this? Most statistics are reported with margins of error. Margins of error provide an estimate of an accuracy. Estimate of accuracy, most journals require them. Somebody had asked about this, but here's an interesting thing about the margin of error. Basically, we use the margin of error to create our own empirical rule for our particular sample, right? With its particular mean. So basically what we're doing is just taking these values and creating this same kind of confidence interval that we have when you're using this empirical rule, because again, we have that 95% confidence limits, right? We know that 68 95% of all values fall between plus or minus 2 standard deviations of the mean. So we're kind of doing that here to we're adapting it to our particular sample here. We're going to talk more about the standard error in this next lecture coming up here. Confidence interval, okay, so it's an interval in which we believe with some level of confidence, whatever it is, right, that we will find the true population mean value because we are, when we calculate values like say a mean, that's just a point estimate, right? A point estimate, but the interval gives us a wider range of possible values. Like in this case here, let's see, they were collected from 100 Pipersville student adolescent males, age 21. The mean on the Jeffrey body weight index for these 100 males is 70. Okay, so that's the point estimate, right? But we know with 95% certainty that the true population mean value is somewhere between 67.08 and 92.94 rather than 70 is just an estimate. It's just an estimate. Correlations, why do you need to know this? Correlations are measures of effect, an effect size for the sample of the relation between two variables. Correlations may imply causal relations, but they are not the same as causation. A correlation is a standardized covariance. We use covariances a lot, but in that they're not very interpretable because you have to know the scaling. When we standardize them, dividing them by the standard deviations of each variable, we get the correlation. This is a beautiful picture of different types of correlations. This is positive. Positive goes from left up from left to right. Negative goes down from left to right. And the amount of spread we have determines how strong our correlation is. When all the dots are on the line, we have a perfect correlation. As it gets spread out, the correlation gets lower and lower. Correlations can be positive and negative. That sign doesn't mean anything other than the direction of the relation. So this is going up from left to right, so that's positive. This is going down from left to right, that's negative. But as far as the strength is independent of the sign, right? So like this value point, negative 0.9 is much stronger than a positive 0.5 because we're ignoring that. And those correlations apply to continuous variables. When we lack a continuous variable for whatever reason, either just the variable is not distributed normally, or we have we have we have we we have non-parametric data, things like, for instance, ordinal variables, etc. We have to adapt to that. And one of the types of correlations we can do is a Spearman correlation. Okay. And I talked about whereas a Pearson correlation requires a linear relation between the two variables. Like you see here, these are lines, right? You see lines going through here. A Spearman correlation does not. It just requires that we have a monotonic relation. So you can have changes in slope, but you can't have changes in direction, right? So it's a more robust statistic, much more robust statistic. Just pause this for a second. All right, so why do we need to know about common statistical tests? Well, because we use them all the time, and as you read articles, you'll see a lot of statistical tests. You won't always see this specific one. Hey, we're doing the z-test, but the z-test could be employed within other statistical tests, just as the t-test is. Like in a regression analysis, we use t-distribution. The z-test is used when we know the population standard deviation. This is the equation for the z-test. We're going to be doing all of these over the course of the semester in some way or another, talking about them at least. The t-test is used when we do, well, at least the one sample t-test is used when we have a small sample size or we don't know the population standard deviation. So we can replicate this test here, comparing a sample to the population if we don't know the population standard deviation, right? The t-test looks like the z-test. Here you can see it. So these are just related to the degrees of freedom of the tests. Basically, we're talking about the sample size, right? 1 degree of freedom would be a sample size of 2. Usually you lose a degree of freedom when we're estimating something. We're estimating something in a population value from a sample. So here we lose degree of freedom as we go along, but you'll notice that this is akin to the sample size, right? So this is 2, 4, 9, 21, etc. If we're losing 1 degree of freedom, that's really the sample size. And as it increases, you'll notice that these converge. There's a convergence to normality, where the black line is a standard normal. The difference is you see the tails are wider in the t-tests, right? But they still all go to infinity. Infinity and beyond. So like I mentioned, this is a one sample t-test. So anytime we're comparing a sample to a population, because we don't need to know the population standard deviation, we can test anything. Like I was riding my bike today, I might say, oh, a good time for this course is whatever, an hour and is 1 hour, and you were a little bit above that. Is your if I was represented by a sample, not just one person, I could compare my sample to that population value, see if I had significant difference. Paired sample test is when we're comparing repeated measures on an individual, but just two repeated measures, right? So we're comparing pre and post in some kind of a drug, or we're comparing uh, two different wines or two different sodas and seeing that people like them. It's the same person being compared twice. This test looks exactly like the one sample test, except for you see these little deltas here that represent differences, right? That's all the only difference between those two. We use the independent sample t-test when we're dealing with two separate samples of different people. And there's different ways to do this. I like to use this specific equation. This specific equation is for an independent sample t-test when we don't know if the variances are equal. So this is actually based on not assuming equality of variance, right? But it's a little bit more complicated than if we assume equality of variance. You just need to know that there's a difference in the two. So we use a different denominator. This denominator, or our standard error, is just a little more sample specific than it is when we're using the test that assumes equality of variance, and then we use something called a pooled standard deviation, or pooled variance, sorry, and then we use that to calculate the standard error. To calculate the degrees of freedom using this test, we have to use Welch's degree of freedom. It's just a little bit more complicated to calculate. Thankfully, the computer does everything for us. In fact, here's a nice little output for a computer result. I think we were comparing males and females in body mass index. And what this does, this is very common, and this was done in SPSS, although we use SAS. I use SAS now in my lectures. And then LaSalle doesn't have a contract with SPS anymore, and there's other software, but they are all the same. The first thing they do is test for equality of variance. Once you complete this test, either you'll assume equality of variance or not assume equality of variance. So in this case here, this is called Levene's test for equality of variance. It's an F test, which is one type of test, and we look at its p-value. This is what SIG stands for, p-value. It's a probability of the observed result given the null hypothesis is true. So assuming the null hypothesis is true, is a value this large or larger statistically significant? And if we use a criterion of 0.05, which is a very, very common alpha, and we'll be talking about that soon, we would fail to reject the null hypothesis. So this is the null hypothesis for Levene's test. It's the variances are equal. That's our null, and that's one we'd like to reject. This should be H1. I think I said that in class. H1 or H sub A or whatever. This is the alternative hypothesis. We'd like them not to be equal, or this is in this case doesn't really matter what you like. The computer does everything for you. So in this case, since our alpha is higher than 0.05, it's higher than 0.01, and this is a large sample, so we definitely want to use 0.05 here, or 0.01, depends. But generally, we do 0.05 for this equality variance test. We'd fail to reject it, therefore we can assume equality variance. This is a situation where you probably, I guess you prefer not to reject the null. Okay, so now we move on to the t-test, and these are our t-test results. So here's our t-test value minus 2.839, and they're pretty similar. Degrees of freedom are different because of the different calculations. For the test, assuming equality variance, we just add the sample sizes together and subtract 2 from it in this case, right? And then here's our p-values. Depends on whether you have a 1 or a 2-tail test. Like if our alternative hypothesis for this test, here's our alternative hypothesis. If it's one tail means it's directional. Like mean of group 1 is less than the mean of group 2, or the mean of group 1 is greater than the mean of group 2. Those are one tail, right? There's one direct. You pick one or the other. We'd use one, we'd have one p-value. If we have a two-tail where we don't know if there's going to be, we don't know the direction of the relation, right? What's going on, the direction of the effect. Like I think that was males and females. Are males have higher, what is it, body mass index than females, or females and males? We don't know. We generally do a two-tail test, right? The one-tail test, and we're going to learn about this more soon. The one-tail test is more powerful than the two-tail test, meaning you're more likely to reject the null hypothesis with a 1 than the 2. In fact, two-tail p-value is twice the one-tail p-value, right? So these are twice as large. This is probably 0.0025, right? So it's just half. So you see the one tail is half of the two tail. Lower probability is better. You get the mean difference here. You get the standard error of the difference, and then you get the confidence intervals, okay? For the mean difference. That's your prototypical test result. Let's see. We often in statistical courses, you use critical values rather than p-values. So when I was evaluating this, I'm looking at the p-values, how they relate to whatever my alpha is. But in an actual course, you generally look at critical value, something that's given to you from a table, and you compare your result to the critical value. P-values are just more efficient because computers spit them out. Why do I need to look at a critical value when I get the p-value? P-value is just more efficient. ANOVA, this is when we're comparing more than two groups, right? More than two groups. And ANOVA is what's known as an omnibus test. So the test will give us whether or not we have statistical significance, but won't tell us where the significance is. Like I say, I'm comparing several things. I might want to, well, let's just look at this example. Suppose we were conducting an experiment to test high, moderate, and low dose sunshine pills on happiness. These two doses are compared to placebo. So if I get a significant result, it's going to tell me that there's a significant effect somewhere here. But I might want to know, is the high dose better than placebo? Is the moderate dose better than placebo? Is the high test better than the moderate dose, etc., right? So I might want to know where the effect is. The problem, though, is that if we just start looking at all possible pairwise comparisons, we're going to increase the probability of a type 1 error, a false positive result. How that is done is we can actually calculate the number of possible pairwise comparisons using this, using this equation here. This is a binomial coefficient. And you can see how I did it here. In this case, with the level, there are 4 levels with 4 levels. And if I'm making all pairwise comparing pairs together, I can make 6 possible comparisons. That would inflate my type 1 error. Let's say alpha is my probability of a false positive result. I set it at 0.01, but if I were to do 6, so that applies for the overall test, the omnibus test. If I were to conduct all 6 tests, I would inflate that probability from a 1% chance of a false positive result to a 6% chance. Doesn't seem like a lot here, but that's a 6-fold increase. Let's see what else. Bonferroni correction is one of the many types of corrections you can do. A Bonferroni correction is simply dividing the alpha by the number of comparisons you're going to make, and then using this as your alpha for each comparison. Our alpha dictates where the critical value is for determining statistical significance. Okay. So as you can see, the more comparisons you do, it becomes a little more difficult in this case right? Because to be statistically significant for the overall test, my p-value, probability of the observed result given the null hypothesis is true, probability of the observed result or greater given the null hypothesis is true, is 0.01. But if I'm doing 6 tests, it's 0.00167 for each test. Collectively, that makes the alpha 0.01. Okay. Talked about regression. Regression is a type of analysis where we make predictions with some error. Generally, when we do regression, we either do simple or multiple regression. Simple regression is probably very rarely done, although I did it for a paper I'm working on right now just because I wanted to show something. That's one predictor and one outcome. But when we have more predictors, we have multiple regression. This is an example of some kind of multiple regression where our dependent variable, our outcome variable is self-esteem. And these are the different predictors: sex, free or reduced lunch, depressive symptoms. And we can see the effects. There's a strong relation between a correlation and a regression coefficient, right? So these are regression coefficients. These indicate what effect a change in the predictor variable has on the outcome. And then we also get the level of statistical significance using p-values here. If I were to look at these p-values, if my alpha is 0.05, there's only one significant effect here, and that's depressive symptoms. So to read this, you can use this b value, this regression coefficient, and say a 1 unit increase in depression results in a 0.063 decrease in self-esteem, holding all these other variables constant. I can also standardize these regression coefficients so that I can directly compare them. These have no scale anymore. This had a scale, whatever the depressive symptom scale was, whatever the lunch scale is, whatever the gender value is, but this doesn't. So I can say, wow, this one is bigger than the rest. 0.73, ignoring the negative sign, just because I'm looking at the strength, is much stronger than the other two. Okay. We can also conduct like R squared. That's a measure of the proportion of the variance accounted for by all predictor variables, and it ranges from 0 to 1. Higher values are better. I also talked about cross-tabulation tables. I showed you an example of a cross-tabulation table. This is generally done when we're comparing two different discrete variables. Usually it's 2 by 2s. I mean, 2 by 2 is very common, but we use these chi-square tests whenever we have any type of contingency table. It doesn't have to be 2 by 2, it could be 100 by 12 or something like that. But 2 by 2 is very, very common. With the, we can call this a contingency table, a cross-tabulation table. With these tables, we can calculate odds ratios. Odds ratios are ratios of odds. Odds are the probability of success divided by the probability of failure. So we can calculate odds ratios. Say, I can say, in this case, this was that cat dancing example. What are the odds for dancing for food versus dancing for reward? And that's what we do here. We just calculate. So it's a ratio of odds. In this case, we got the odds being 6.65. And then from this, we want to add a confidence interval as well. And this is just using the delta method standard error. It provides us a confidence interval. I don't have to go through what that is, but what did I give us a confidence level? Yeah, here it is, okay? And you have a video to show you how this is derived, why that it is what it is. So here we have cats were 6.65 times more likely to dance for food as reward than to affection as reward. And I provide the odds, you always do, you provide the odds ratio and the confidence limit. Again, this is a point estimate. So this is saying that the point estimate is 6.65, but the true odds ratio is somewhere between 2.983 and 14.687 times more likely, right? We can also look at the relation between variables in the contingency table using the chi-square test. Chi-square test looks at the difference between the observed frequency in these cells and the frequency of values expected by chance alone. We square those and divide by the frequency, the expected frequency. We sum across the different cells. So this is summing across the cells. And if there's 4 cells, you add 4 of these together, right? The degrees of freedom for this test are the rows minus 1 times the columns minus 1. If I were in the, I don't know why I had this here. What did I have here? I had some example here. A study conducted to examine whether education level is related to having regular exercise. I guess I didn't provide the table here, but it was a 3x2 table. 3x2 table, because I can tell that there's 3 rows. So the degrees of freedom are rows minus 1, and the column degrees of freedom are columns minus 1. So we get 3 minus 1 times 2 minus 1 is 2. And for a 2 degree of freedom chi-square, we get a critical value of 5.99. And we can use that to judge statistical significance. Okay, so and then let's see. And here I show you how it's done, right? So here's the example, how it's done step by step. There's a lot of calculation involved, but you're going to again use this with a computer, and the computer will spit out a p-value for you to determine whether something is statistically significant or not. So in this test, we got a chi-square value of 0.233907, which is much smaller. What did I do here? Well, it looks like I did 1, 2, 1, 3. Okay, so this should be this critical value should be what I had before, 5.99, but it didn't matter even if it was 3.84 instead of 5. This is for 1 degree of freedom. This is the critical value, but it didn't really matter because this calculated value is much smaller, so we'd fail to reject it. And this p-value is 0.89, which is way larger than 0.05. And then here finally we have a logistic regression. Logistic regression is done when we have an outcome variable that's categorical of some sort. Could be binary, could have more than 2 levels. Now there are different kinds of logistic regressions, but we're not going to worry about that right now. I'll just assume it's binary. And then these are just like with linear regression, you have a model with error, but you're trying to make a prediction. But here we're predicting the odds, right? Predicting odds. And when you read anything with logistic regression, you're probably going to get a table like this, right? The table provides you the parameter estimate, the b value, the standard error, and we use the t-test value for linear regression and multiple linear regression, right? With continuous outcome, we use a wall test here for the outcome. This follows a chi-square distribution, ironically, or interestingly, not ironically, interestingly, it follows a chi-square distribution. These b values are what are known as log odds. If we exponentiate them, we'll get our odds ratio. So that's pretty cool. And then we get confidence intervals for the odds ratio. So in this case, we were looking to I think we were predicting alcohol use to understand the effects of self-esteem on 30-day alcohol use. One is used and one is did not use. So we see one of the significant predictors was 30-day smoking. If you smoked, you were 2 times more likely to drink alcohol, with the odds ratio being anywhere between 1.726 and 2.564. Our point estimate was 2.104. And what else do we have here? Looks like self-esteem was marginally related, right? I can tell, well, it has a p-value of 0.09. So it looks like I used a 95% confidence interval. That means I used an alpha of 0.10. The two are complementary, the confidence interval and alpha are complementary. So at 0.10, there was 2 significant results because these p-values are less than 0.10. Okay. So that's what's called the logistic regression analysis. And that, my friends, is the remainder of the review. You please, read over it, read over the notes, look over everything, and enjoy. I mean, we'll be covering most of this stuff in little bits and pieces throughout the rest of the course. Okay, let me stop share. Thank you very much. See you soon.